Get going. So welcome back for session 11. This week we'll be talking about chapter 2 from a mathematical introduction, but first we'll be covering some questions from the last week and the homework exercises. Before we kick off, I think I remember seeing a question from Skonov on earlier this week on Carmichael numbers. And the question was that the FLT criterion for all integers b, which I believe is Fermat's little theorem criterion, for all integers b which are relatively prime to some value n. The question was, are there numbers which satisfy the criterion for not for all elements b? Are they more common than the Carmichaels? And I'm not entirely sure what this question is actually asking, but just a quick bit of background on the Carmichael numbers. The Carmichael numbers are an edge case to a sort of naive primality check that we might just use Fermat's little theorem to check whether a number is prime by taking any number a to the power of n minus 1, where n is the suspected prime, and see if a to the n minus 1 is 1, then that is evidence in favor of n being prime. But the Carmichael numbers are a sort of thorn in the side of that approach, in that only numbers that are factors of a Carmichael number or are not co-prime to the Carmichael number will actually produce the desired check for that potential primality check, rendering it not very useful. So the question that I think Skonov asked is that Carmichael numbers satisfy the FLT criterion for all integers b. What that's saying, if I was to just quickly draw that, the FLT criterion in this case for prime candidate n is that for all a to the n minus 1 mod n is equal to 1. And in the case of Carmichael numbers, all a such that the GCD of a and n equals 1 satisfy the FLT criterion. And I think I see Skonov is here today. Did that answer your question, Skonov? All right. Oh, cool. Great. Then moving on, I wanted to quickly go through the solutions from last week. So there were a couple of exercises for last week. Last week should be reasonably a review of some stuff, but there were a couple of pieces that were new. Excuse me. The sort of basic algorithm that we use to compute large exponents, which is maybe not must-know knowledge on how to implement, but it is fairly fundamental to know how we're actually working in these massive fields, is that we need to know how to compute exponents efficiently. So the fast powering algorithm is the way that we efficiently compute exponents over large finite fields. And the algorithm itself is really quite simple. The only annoying thing is getting set up. So the first, say, 10 lines of this code are just checking for bad inputs. And the algorithm itself, starting here, is written imperatively, is quite simple. We just loop over the values of the exponent that we actually want to retain, and we can fairly efficiently compute large exponents in logarithmic time. I won't really go into how this algorithm works today, since I think we covered it a bit last week. But I wanted to give this code as a sort of opportunity to look at so that it would be available. Then for proving exercise 1.11, the proof is reasonably straightforward. It was intended to be an opportunity to practice doing a proof that wasn't particularly challenging, but demonstrates some fairly basic understanding of um, the extended Euclidean algorithm. So if you'd like to see and compare your effort to this proof, I would invite you to do that, since thinking in proofs is sort of a fundamental skill, and this is a sort of good introductory challenge to it. The same sort of thing applies to the exercise for proving that the greatest common denominator of A and B equals 1, which is a sort of expansion of Fermat's little theorem. So then, if you are familiar with Fermat's little theorem, this should not have been too challenging. So moving on to the course notes, or maybe before that, quickly I'll ask if there are any questions from the chat this week before we move on to this week's topics. Okay. So moving on to this week then. So we were covering section 2 or chapter 2 in a mathematical introduction to cryptography. So this week's sort of focus is going to be on a couple of interesting algorithms from chapter 2. I won't read the chapter back to you, but I will present a couple of sort of big ideas from the chapter, starting with the sort of trapdoor nature of the discrete log problem. I'll give an example of how the discrete log problem is applied in an entirely different context than encryption. And we'll talk about Elgamal encryption. And then finally, we'll round up with a quick example of the Shanks collision algorithm. And if you remember earlier back in the course, cryptography, there's usually a collision algorithm somewhere. So we're going to talk about the collision algorithm for discrete log at the end of this lecture. So moving on here, talking about discrete log, the big sort of idea in discrete log, as we've kind of talked about, is that going from some message space to some ciphertext space should be easy. It should be easy to encrypt a message, but very hard to decrypt it without the secret information. And so the discrete log algorithm is basically exactly this picture. And there have been other systems like RSA, and I believe it there was a study into knapsack problems that the book mentions in the 80s by Whitfield Diffie and Ralph Merkle of Merkle tree fame. But knapsack problems, while being suspected to be NP complete, are not adequate because they have extra structure that makes them vulnerable to attack. And if you'd like to understand exactly what I mean there, it's really not so important. But chapter 6 goes into some discussion of the knapsack problem and why it was unsuitable for cryptography. And since I think you've all been exposed to the discrete log problem before, we're actually going to go on something of a tangent now and talk about shared reference strings in zero knowledge. And so a shared reference string is a set of elements. Say that this is an n element long ordered set whose elements are g to the s, g to the 2s, and g to the ns. And if you're particularly familiar with zero knowledge, you'll think, wait a minute, that's not the usual common reference string we use, or shared reference string. They mean the same thing. well, and you'd be correct, but of course, as we're about to get to, we can use the discrete log problem to construct whatever form of shared reference string that we want to construct. So this particular shared reference string is constructible simply by saying if we want a group of people to share some secret, it would be trivial for Alice to say, I'm going to pick S, and I'm going to compute all of the values from g to the s to g to the n times s. But what if we wanted multiple people to compute this, to contribute to this secret, such that no individual party knew the exact value of s because every party had computed and contributed some randomness to it. And it turns out that that's entirely possible. And this is sort of why trusted setups work in zero knowledge. And the core thing to keep in mind is that because the discrete log problem is hard, the thing sitting in the exponent right here is effectively hidden. So we can think of computations on the exponent as computing behind a hidden wall. So if Alice and Bob wanted to collaborate to choose some value s, where s equaled sa plus sb, then the way we might do that is that Alice might choose her value SA, and Bob might choose his value SB, and they might both publish the sequence. We're going to use capital scripty S. That's a more, okay, yeah, we're going to use capital scripty S for the sequence. SA equals that, and SB is going to equal that. So if Alice and Bob publish these sequences SA and SB, obviously Alice could obtain Bob's string and say, I'm just going to infix multiply all of these elements together. And the outcome of multiplying each element together would be simply multiplication would produce this common reference string. And Bob could do likewise. And the neat thing about this approach is that now both Alice and Bob have some exponents, SA plus SB, and 2SA plus SB, and all the way up to there. However, neither Alice nor Bob can recover one another's value for SA. So Bob cannot recover SA, and Alice cannot recover SB. So this would be an example of using a form of multi-party computation to produce a different kind of shared common secret. And what's quite neat about this is that if we wanted to produce this kind of shared common secret, we can actually evaluate entire polynomials behind the hidden exponent of the discrete log. And it's worth mentioning that the discrete log problem in this context is presented over the integers, where we're dealing with exponents, but the entire problem plays out in exactly the same way over a general group, which is to say that if we want to use these techniques over an elliptic curve group, we can use them just as easily as we can over finite fields. Now, I'm not sure if I've lost anyone yet, so I think I'm going to pause now for questions. Okay, seems good. So in that example, we established that Alice and Bob can collaborate to generate secrets SA and SB behind the hiding of the exponent. But why would we even want to do that? And it turns out we can do other things too. Besides multiplying g to the SA times g to the SB, Alice could, say, exponentiate each of Bob's values by saying that, what color did we use for Alice? We used blue. We'll keep up with blue. I think I switched later, which is okay. So if Alice sees that the first element in the array is g to the SB, then Alice can simply say, take g to the SB to her secret value, g to the SA, and then they have g to the SA times SB. producing the second kind of common reference string they might be interested in producing. But if we want to get really powerful with this, then we might actually want to produce a common reference string where the shared secret is taken to exponents. The reason this is powerful is that we can then compute entire polynomials in our hiding of our exponent, which I'm hoping to show it to you in just a second. But this demonstration of this second thing that Alice could do is a way of saying, or is intending to demonstrate that the hiding in the exponent is a very powerful and flexible technique. If the structure that Alice and Bob need to produce their system is they need the additive secret times some constant times some scalar, they can do that. If the form they need is the multiplicative product times some constant, they can do that. Or if they need the powers of their shared secret, they can do that too. So this is a very flexible technique for establishing shared secrets between parties. And now we're going to get to why this particular technique in this line is quite powerful. Okay, I think I made the remark. Very useful form. I feel like a government bureaucrat. This is a very useful form. You must not lose this form. But this is a very useful form for computing polynomials in zero knowledge. And you might be familiar with the term polynomial commitment scheme. This is exactly what's being done oftentimes when we're working with polynomial commitment schemes, is that some polynomial is committed behind the exponents of some value of some exponent, or some polynomial is being committed in the exponent of some generator. And you might ask, well, how would we even generate this string? Well, as before, we can have Alice and Bob publish some string. I might have not left enough space here. Oh, okay. So as before, we can have Alice publish, instead of Alice publishing the original string that we said, I'm going to grab this and copy that, scroll way down, and then we're going to paste that there. Okay, yeah. So this was the original. We're going to change this up such that instead of the original string that Alice published, Alice is now going to publish the values g to the SA, g to the SA squared, up to g to the SA to the n, and Bob is going to do likewise. Bob is going to compute g to the SB, g to the SB squared, and g to the SB up to the n. Now, when we multiply these two strings together, what we get is g to the SA plus SB, g to the SA squared plus SB squared up to g to the SB n plus SAN. But if we instead say, this is less useful because what we would actually like, what we actually want is g to the SA plus SB. That's awful handwriting, I'm sorry. G to the SA plus SB to the n. And we can do that simply by saying, instead of multiplying together, we can do as before, exponentiate. And you might be thinking, this is a lot of exponentiation. I hope that's not an expensive operation. And this last week's exercise hopefully demonstrated that we have this fast powering algorithm. We do a lot of exponentiation in cryptography, so we need that to be fast. And we have a way to do that. There are techniques that I probably won't get to discuss in this course for doing quick multiplications over fast Fourier transforms or the Montgomery multiplication algorithm and so on, which are each interesting in their own right. But I don't think we'll have quite time enough to talk about some quadratic algorithms for multiplication. So back to this, instead of doing that, we can instead exponentiate and say that g to the a, this is Bob doing this, g to the a, I guess sa to the sb is of course just equal to g to the sasb, and g to the sa squared to the sb squared is simply equal to g to the s a s sb squared, or shall we say squared. And then the shared secret would be the product of SA and SB. Neither Alice nor Bob could compute the other's secret, so Alice could not compute SB. And let's say now that S equals SA times SB for simplicity, we can compute a whole polynomial in the exponent. So if the polynomial p of x equals a0 plus a1x to the 1 plus an x to the n, then we could simply say that everyone has the secret g to the s, where no one knows s, g to the s squared up to g to the s to the n. So we can compute g to the p of s. So we can compute any polynomial of degree less than n, less than or equal to n in the exponent, and say that g to the s to the a0 times g to the s squared to the a1 plus g to the sm to the an is simply equal to g to the a0s times g to the a1. I suppose I should have shifted these guys down one. I'm actually off by one. Sorry about that. A1, A2, what is this, N? I guess that's still N. All right. So, yeah, A1, A2, S squared times G to the S, N, A, N, which is simply equal to G of to the P of S, as stated before. Now, that was a pretty fast example. The intent there was to say, give some sort of intuition for why the discrete log sort of problem is very generally applicable in cryptography. It gives us a fully flexible way to hide whatever we want in whatever form we want in the exponent. And there are, of course, security bounds on that. But the discrete log is such a flexible problem. We can kind of do multi-party sort of hidings of secret information. We can have Alice and Bob obtain secret information if they're choosing. We can combine that information in very flexible ways. We have ways to do multiplication and addition in the exponent with shared secrets. We get a lot of power there. We basically get the full power of field computations in the exponent, which is very powerful, or nearly the full power of field computations. So the tangent on shared reference strings is a sort of demonstration of why the discrete log problem is so powerful for cryptography, because we get to hide all sorts of stuff in there. It's like if you sort of watch TV, it's like the clown car that you can stuff all the cryptographic secrets into the exponent with reasonable security. And that's basically the end of the tangent. So I think I'll pause there. Any questions about the discrete log problem before we get to talking about the Elgamal cryptosystem? I could move this out of the way. I should have done that a while ago. Sorry. should we check that G is a generator in the group here? Um, yeah, well, so we generally assume that we've picked some generator G of a group or subgroup of sufficient order. But it's generally assumed that we can choose G as we would like um, over arbitrary fields. We're generally looking for G of order 256 bits. Whether we're working in a field with a prime that's much larger than 256 bits or a prime an elliptic curve group. We want 2 to the 256 bits because we're going to get to Shanks' baby step algorithm, which demonstrates why working over just 128 bits would be obviously insufficient. The algorithm we discuss at the end of the day will kind of demonstrate that. Could you comment a little on how setup ceremonies and decentralized protocols relate to what you just described? Yeah. So the setup ceremonies for, let me scroll back up just a bit. The whole deal with setup ceremonies is that we're trying to produce this common reference string, G to the S up to G to the, well, we're usually going for something actually like, where'd it go? There we go. We're usually trying to produce something of this form, where either this addition or multiplication or whatever it happens to be produces some common shared string where no one knows the value of the combined secrets. So everyone contributes their little bit of randomness in their secret. And that's particularly useful for common reference string stuff because it, like I mentioned earlier, it lets us commit to polynomials in the exponent by hiding them. But if, for instance, we're talking about zero knowledge protocols, the usual scheme here is that we need to basically prove some function has evaluated in such and such a way, but we want to give the shortest possible proof to verify it. And it turns out that verifying something in the exponent, even if you don't actually have to compute the entire polynomial yourself, there is a sort of probabilistic argument that the prover can prove that they've computed something honestly and that it's consistent with the non-hidden version of that polynomial. So back to setup ceremonies and decentralized protocols. In a setup ceremony, just like in the above example where Alice will choose secret A and Bob will choose secret B, and they'll both publish their choice of the shared reference string. And then they'll compute the other's version of the shared reference string after exponentiating or multiplying together or whatever the protocol specifies. A common reference or a decentralized protocol for setting up a shared common reference string would be basically this, but ideally with more participants than just two. Because obviously if I'm Charlie and I don't trust Alice and Bob, I would probably like there to be, maybe tens or even hundreds of people that contributed to the shared reference string if I don't know any of them. But as far as the security of shared reference string schemes go, as long as one party is honest in the shared reference string scheme, it's basically impossible to recover the shared secret that generates the common reference string. So as a security assumption, trusted setups do require many participants, and you need you would like there to be many participants specifically so that you have a reasonable confidence that at least one is honestly contributing randomness. I tend to treat common reference strings as a very sort of weak security assumption, and that like it doesn't seem entirely hard. It doesn't seem hard at all to sort of grab 200 people that would contribute some randomness and assume that at least one of them is not cheating with the others. So that might have been a bit more than what you asked for, but that's sort of how common reference strings are established. Maybe we'll talk about BLS protocol as a sort of example of that in week 15. That would be probably a good example. In my previous life, I was working on threshold crypto systems, so I could talk about those for kind of a while. Uh, okay, cool. That covered it. All right, awesome. So if we were to switch over to talking about the Elgamal crypto system, there are a couple of things that are good about the Elgamal crypto system, and one of them is that it's a particularly good example of discrete log. So it makes for a good second example after that previous one. How you would use it to construct a encryption scheme. Unfortunately, for Elgamal, it is not efficient. That is, we will need to send not one, but two ciphertext elements. So there's at least a two-factor blowup in how much ciphertext that we send versus how much plain text we recover. So if we wanted to think in terms of efficiency, we ideally would like to send no more ciphertext than there is plain text. That is, if there's 372 bits of plain text, we would like to send 372 bits of ciphertext. So this obviously doubles the ciphertext to plain text ratio. So that's not super efficient. The second thing is that it uses this ephemeral key K. And as far as implementation details go, this is not an issue from a theoretical level that Alice and Bob should be able to choose some randomness. But from an implementation standpoint, anytime you ask the machine for randomness, there's an opportunity for an adversary to game poorly implemented randomness. And of course, if the encryptor sends reused nunces, nunce recall means number only used once. There is always a sort of assumption that the implementer is sufficiently competent and that the randomness source is sufficiently difficult to extract from the adversary's perspective. This algorithm works, but it is a demonstration of there are a couple of things about it that are not desirable, so we can come up with more efficient crypto systems. So back to the sort of question of how to set up Elgamal encryption. So very simply, if Alice is going to encrypt a message to Bob, and Bob has private key lowercase b and public key capital case B, these are fairly common conventions. We often say that Alice's public key is A, capital, and Alice's private key is, or secret key is lowercase a. We can sort of assume that this is a well sort of known syntax. So we would just simply compute Alice's, given that Alice wants to send message M, Alice can simply send the tuple, the two-valued tuple G to the ephemeral K, mod P, and M times B to the K. And now for Bob to recover the message, we observe that C2 is simply the message times some hiding. So we just need to get rid of the hiding. So we can get rid of the hiding by multiplying C2 by B to the negative K. And then, of course, B to the C2 times capital B to the negative K is simply M times B to the K minus K, which is just M. So if Bob has a way of recovering B to the negative K, then, of course, Bob can decrypt. And Bob can compute B to the negative K. And this is a good sort of opportunity to check whether you understand the significance of the extended Euclidean algorithm, which I suppose I've hammered at length. The significance is that if Bob has B to the K, then Bob can compute B to the negative K. And that is, the extended Euclidean algorithm means that it's easy to compute inverses. But how does Bob get B to the K? Well, Bob simply says, well, I have C1, and I know my secret key, lowercase b. So C1 to the power of my secret key is simply B to the K. And now with B to the K in hand, we can compute B to the negative K by the extended Euclidean algorithm. And then by the reasoning above, if we have B to the negative K, we can simply multiply C2 by B to the negative K and recover them. And that's how the Elgamal encryption system works. I think I remember the first time I saw it, I was a little bit overwhelmed. There's a couple of moving variables going around, but I think it's a very elegant algorithm in that it demonstrates an encryption system that relies on the difficulty of discrete log And if you understand Fermat's little theorem and the extended Euclidean algorithm, this neatly ties together all of those pieces, and we can recover a crypto system that is fairly straightforward to understand. Did I mention Fermat's little theorem? I'm not actually sure why I mentioned Fermat's little theorem. I'm sure there's a reason that it exists in this case. But, well, I guess I used it in my example. But I think this week's exercises are centered around using pen and paper to get some sense for actually executing these algorithms. Since they're not entirely practical, and you won't ever really see very many production implementations of, for instance, Elgamal or Shank's algorithm, but they do give a sort of good opportunity to practice with pen and paper. So as an optional exercise, I've published the 2 exercises for this week are to compute Elgamal and compute Shank's algorithm, which we're going to talk about next, and then optionally to implement one or both of them. Finally, I think it's time to talk about Shank's algorithm. But before we get onto that, do any of you have questions about the section on Elgamal? Okay, quick sanity check. I have made an effort to color in consistent ways. Has that been useful? Feel free to comment in the chat. I am going to continue now onto Shank's algorithm. See some comments here. We're going to get onto a example of Shank's algorithm. And so Shank's algorithm is this. Colors are wonderful. That's great to hear. We're going to get onto Shank's algorithm here. And the core premise of dealing with Shank's algorithm is that if our exponents lie in some prime field, say 1 to p, we can solve the discrete log problem in at least the square root of p steps. That is, we can solve it in no more than the square root of p steps. So if we're computing over some prime of 256 bits, some prime field of 256 bits, then we can solve the discrete log problem in 128, 2 to the 128 steps. So obviously, Shank's algorithm is a sort of like core insight into how collision algorithms work. There's one other algorithm in the book in what I believe to be a section 4.3 or 4.4 on the Pollard row attack, which gives another example of how to compute collision algorithms. But both of these results are basically that we can do searching in at least square root of n time. And as section 2.9 points out, which we will not be covering, section 2.9 is at a sort of higher mathematical level than I think some of the sections that we are covering. The Pollard-Hellman algorithm in combination with the index calculus, which is given in section 3.8, present sort of what I believe to be the best known attack against the finite field version of discrete log. But they're a bit entrenched, so if you are interested, I invite you to visit that on your own time. So onto Shank's algorithm. So the basic premise is that we're going to demonstrate this with a prime p equals 83. And what we would expect here is that by Shank's algorithm, we would expect there to be on the order of square root of p operations. So we would expect there to be some multiple of 10 operations. And the exact operations here are that we need to compute 10 values here, 10 values there. So we're starting at a constant multiple of 2. And then we need to look for collisions between the left side of the table and the right side of the table. And of course, that's simply a matter of sorting. And sorting is a n log n operation, and possibly even better than that. So if we expect, and where n is the square root of p here, so we would expect 10 computations of exponent, 10 more computations of exponent, and then a search for collisions, which is simply a matter of sorting. So we'd expect this to be quite efficient. We could expect this to be to take if we're working over some prime field p, we would expect this to take on the order of p, or square root of p times, I should write this down. We expect the Shanks algorithm runtime to be 2 times the square root of p values in the table plus sorting the table, which is going to be square root of p log square root of p. So all of that is to say that this is going to be a relatively quick algorithm if p is small. And so the example here that I want to give, we simply compute. If we wanted, if the question was, could you compute the value of 2 to the x equals 3 mod p? How would you go about it? Well, to solve this, we might observe that let's grab purple. Purple's a great color. We might observe that 2 to the x mod, let's go here, '83. We would simply observe that, say that x equaled 10 times a plus b, then g to the x equals 3 would be equivalent to g to the 10, what is this? G to the, I think we say b would be equal to, more mod p's here just for completeness. This is darker than I think I usually like, so let me know if this is hard to read. So g to the b here would be congruent to g 3 times g to the negative 10a. And then what we're going to do here is we're going to generate our table for these values and these values, varying a and b over 1 up to the square root of p, rounded up, which in this case is 10. And that's exactly what we do above. And the reason that this is significant is that if we compute a table for these values on the left, these values on the left, and these values on the right, and we find a collision, then of course we can conclude that we have found values for a and b, and therefore we have found the value of x. Skonov has asked, is it giant step, baby step? Yes, indeed. It is step, giant, baby step, or giant step, baby step, or Shanks baby step, giant step. Though this is really mostly just a fairly basic collision algorithm. I'm surprised that it has a name, in that collision algorithms have been sort of known about for a while. They're sort of generic attacks, so I just think of this as a collision algorithm. So back to the example. It's relatively trivial to, let's grab a terminal here and do a demonstration. This is a really quite simple problem to solve. So let's grab Python. Now, what do we want? We want to compute all of the powers of 2 to the exponent. So we're going to say for I in, we want 2 times I, 2 times, let's say for x in 2 times x mod 83. Let's say this. For I in range 10. If print 2 times I mod 83. And so there's our values on the left side. And I guess we need to go to range 11 as opposed to 10 because we want to have 10 inclusive. And then second, we can do this exact same thing for I in range 11. Print 3 times, what would you say? We said 3 times 3 to the I, yeah. Because on the left-hand side, here we compute exactly what those values for H and to the negative 10 are. We determined they're just 3. So what did we say? 3 to the I mod 83. That is all correct. And then of course we can generate the table on the left-hand side, and we see that 4 appears in both of these rows, and we have solved the problem. I hope this text is large enough to read. But that is all to say that this is a demonstration of quickly solving with almost pen and paper. Python is almost pen and paper, the sort of Shanks baby step giant step algorithm. And that's pretty much all I had. Oh, and then we recovered that because we see that the value for left-hand side is simply 2, and the value on the right-hand side is 7. We have established that, I think, what did we say? We said, I get 2 from. I'm actually not sure if I did this example right, so ignore that. We have established values for A and B such that we can recover X from that statement. So yeah, and that's pretty much all I had prepared for you guys today. So before we leave off, let me make that bigger. Last chance to ask any questions before we call it a day. Yeah. Okay. Thanks everyone for joining. Sorry that it's sort of taken me a while to get this this session's notes out. This week was kind of chaotic. I don't think I've even published this yet, so we should do that. So yeah, I'll see.